What's up? It's Alan. Double angle identities is what we're going to get into today. So hang in there. I'll derive them. We'll do some examples. And hopefully you'll get the hang of these as well. So without further ado, double angle time. So in this first section here, dealing with these double angles, we're going to be talking about cosine first. We'll go ahead and start with that because we already initially started with the cosine sum formula. And so what we're going to deal with is rewriting 2a, again, not changing the value of it, as a plus a, because now it looks like the sum formula. Now, unfortunately, as you can read here, we're going to actually have to get a little creative because there are 3 different versions of this that we'll get to. Okay, so let's start with the first one here. I'm going to rewrite cosine of a plus a as its identity, which is cosine of the first, cosine of the second angle, which again happens to be the same for this, and then minus the sine of a times the sine of the second angle, which also is a. So I can actually rewrite this as the cosine of something times itself is the cosine squared of that thing, minus sine squared. And that is one of our 3 derivations. Now you may be noticing some squared terms, which alarms should be going off thinking of Pythagorean identity. So I'm going to go off to the side and refresh your memory on what that is. And because we have the sine squared plus cosine squared of some angle is equal to 1, well then hopefully you can see why we have 2 other identical identities to cosine of 2a. Because I could then solve this equation for cosine and substitute that in here to get an alternative version, or vice versa, the sine squared. I could derive this by subtracting that over and substituting that in there. So I'll do that now so that you can have all 3, and then we'll move on to sine and tangent. So taking my sine squared plus cosine squared of an angle equals 1 and subtracting over the sine squared, I get that cosine squared is equal to 1 minus sine squared. So I will take that and substitute it in place of that, keeping this the same, to get, which then allows me to rewrite and simplify this by getting rid of the parentheses now. And I would have 1 minus sine squared twice. So I would just write minus 2 times sine squared of my angle. Doing something similar for now, sine squared would give me, and so this one you got to be a little bit more careful on. Once I've taken and subtracted over the cosine squared this time, now I would have my sine squared all by itself, since this cancels out, and I'd have it equal to 1 minus cosine squared. So I'll take this, keep that the same, and now I'll replace that with what I know it's equivalent to, which is 1 minus cosine squared a. So I'm actually going to have to distribute a negative to both of those, and that will give me a -1 and then a positive cosine squared. And because I have a cosine squared a there plus another, that means I have 2 cosine squared a's, and then I have this -1. Remember that -1 is not being done to the angle. If you want to throw parentheses around it and put squared instead of there, that's fine too. You can even throw the -1 in front, but this is usually how they'll write it. Okay, so those are our 3 derivations for the double angle formula for cosine. Now we're going to do something similar for both sine and tangent. So if you want to pause and actually derive it yourself, cool. If not, we'll go ahead and do it together. And yes, thank goodness, there is only 1 for each of these. Okay, so there's not 3 different derivations, and you'll see why. Let's go ahead and work out the sine of 2a, which again, we can write 2 a's as a plus a. And that allows us to rewrite the sine of a plus a with our sum formula of sine of the first, cosine of the second angle, which again happen to be the same, and then sine of the second, and then cosine of the first. And if you notice, I have the same thing twice. So sine a cos a plus another sine a cos a. Anything added to itself would then give me 2 of those, which happen to be sine A cos A's. So that is a quick, easy derivation. Let's see what it looks like for tangent. So taking the tangent of A plus A, which is 2A, I can write the first angle plus the second, and then 1 minus the first times the second, which, simplifying that, would yield 2 tangent A's on top over 1. Since these are multiplying together, I can write minus tangent squared of A. Again, the worst one is obviously tangent because it is a fraction, and most of these trig functions that we evaluate come out fractions, but very easy, simple derivations. So let me give them to you all in a nice, concise form. Okay, so there are the 3 for cosine written there together. Of the 3, there's one that we usually do not prefer, and that is because there are 2 trig functions. I'd rather choose the one that has only one trig function. Okay, remember there is only one for sine and tangent, so you have to just memorize those, but you do have options when dealing with the double angle for cosine. Okay, now remember this is an angle. It's unlike a negative. You can't just bring it out if it's an even or an odd function. So please make sure that you don't just pull the 2 out and evaluate your trig function with just the angle A. So there's a few other identities within this section that I'm going to bypass. I just want to mention they are not seen as widely. So if you want to check them out, by all means you can, and I encourage you to do so. They may come into play if you further your career down the road into some of the later calculus sections. Okay, second or third semester, you'll have these product to sum or sum to product. And you can see how nasty these are, which is kind of like a last ditch effort. If we have 2 things multiplied together, and then be better off with the addition of the 2 angles added together, or vice versa. 2 trig functions added together, would it be a little bit better if they were multiplied? Things like that, okay? So sum to product, or even product to sum. Okay, these are the options that we do have down the road, which again, too much to memorize. I'm picking and choosing the ones that are more widely seen, not to say that you will not see either of these or use them down the road. Okay, but at least you're aware of them. We will not cover them in depth like we will definitely see and do with the others. Okay, so don't worry about these in this class, but like I said, you may come across them down the road. So wanted to at least show them to you. So that's it for the notes. Again, short and sweet, just deriving a few of those identities. Now we need to see in more depth how to use them with certain scenarios. So here's example 1. If you want to go ahead and pause it and give it a try from right off the bat here, feel free to do that. We're just going to ask for each and every one of these. I started with sine, then cosine, and then we'll end with tangent. Okay. Now, of course, I did give you some information, but just about theta, not the angle to theta that we're trying to evaluate. So what helps? A drawing. So I'm going to go ahead and start by drawing the sine for that angle. And remember, we have to figure out what quadrant we'd be in. And because it's a sine of some angle and it's positive, we know right then and there that we're in one of those 2 quadrants. Can't be in 3 and 4 because that's where it would be negative. But they have to give us something else because we need to know, is it in quadrant 1 or 2? So they told us that the cosine of that same angle theta is less than 0, which means it's negative. So therefore cannot be in quadrant 1, which means I'm going to draw this in quadrant 2 now. Now remember, when drawing this, it is just for theta. And when I draw that in there, I'm going to put this as a negative, positive, and always positive direction. Then because they gave me the sine of this thing, I will go ahead and know that this is the y and the r and put those in their place. So the y there and the r there gives me a something 817. And again, hopefully that is a Pythagorean triple, but if not, we're going to have to use the Pythagorean theorem to come up with that missing leg, which is our x value. Hopefully you recognize that it is a Pythagorean triple. It is 8, 15, 17, which allows us to skip some steps and go straight to our derivation of the sine of the angle 2 theta. Now, I don't know the sine of 2 theta because the only thing I was given was theta. So I don't even need to know 2 theta because I do know in identity that is identical or equivalent to the sine of 2 theta. It is 2 sine theta cos theta. Remember, we don't want to have to derive and rewrite this as the sine of theta plus theta and then rewrite that and evaluate all 4 things when we only have to evaluate 2. So as long as you have this memorized, then we just need to evaluate those 2 things, which remember, they actually gave us the sine of theta already. So we can just put in our 8/17 right off the bat. And then we also would have to come up with the cosine of that angle theta, which we know is the x over the r. And since these are all being multiplied together, I'm going to put this over 1 and try to simplify anything on bottom with anything on top before I multiply straight across. And since 17s are both prime numbers, and there's nothing up there that is a 17 or a multiple of it, I know I'm stuck with that. So what I'm going to have to do is multiply that all straight across to get negative 240 over 289. So that is my angle 2 theta's answer for sine, even though we didn't have to physically find it because we're able to rewrite it. So that's the power of identities. So if you didn't try that first one, you want to go ahead and pause and try part B. You already have everything you need. All you have to decide for part B is which of the 3 identities would you want to use for the cosine of this angle 2 theta. Remember, I told you one of them you probably don't want to use, but it's your choice. All 3 are identical. So I'm going to choose to use 2 cosine squared theta minus 1 because it's positive and it's an easy one to memorize for cosine of 2 theta. Okay, so the only thing I'm going to actually have to find and evaluate is what the cosine of theta is. That's what I'll plug in there, and I'll still square it, then multiply by 2, then subtract 1, all of the order of operations that we reviewed at the very beginning of the class. So what is cosine of? Notice we changed it to theta from 2 theta, and we have theta. So cosine of theta is the x over r, which is negative 15 over 17. Rewriting and squaring that would give me, and then don't forget we also have to subtract 1, which I'm going to rewrite that as a different looking 1 so that I can actually subtract with common denominators. But before I do that, I'm going to have to double the top. So that would give me 450 over 289. And now when I subtract that 1, which is 289 over 289, I get 161 over 289. Okay, so again, pretty cool that we can actually find those values without even having to know what theta is, or in this case, 2 theta. Right, so part C would be tangent. Let's do that one real quick together, and then we'll move on to the next example. So remember, tangent of 2 theta is the sine over the cosine. So it's the 2 tangent theta over 1 minus tangent squared theta. And then from there, we can then evaluate tangent of theta using that same angle, just being careful with our signs and everything else. Okay, so that would give us tangent of theta is the y over the x, so negative 8/15 for each of those. And now we just have to multiply this out using our order of operations and simplify it. So I'm going to go ahead and write this 2 over 1, and that would give me a negative 16 over 15 on top. And then 1 minus, well, I'm going to have to square this first. Don't do the double negative and get rid of it because you'll make a mistake there. Remember, parentheses, then exponents. Okay, so I multiplied the top straight across, got negative 16 over 15. Now I'm going to square this, which will give me 64 over 225 positive. And remember, we were subtracting that from our 1. So getting a common denominator there is definitely something I could do and then rewrite it, but I'd rather just multiply this whole big fraction by a fancy 1, which I know a common denominator of both 15 and 225 would be 225. So that's the fancy 1 that I'm going to multiply by to both the top and the bottom to get rid of it. Just don't forget to multiply it to the 1 as well. Okay, and that would give us negative 240 over, don't forget the 225, minus, these would cancel out and give us 64. So finishing that off would yield a final answer of negative 240 over 161. So we found sine, cosine, and tangent of 2 theta. That was parts A, B, and C. If I wanted to throw one more thing at you, I could ask you, in reality, you should be able to tell me what quadrant 2 theta is actually in. Because we found sine, cosine, and tangent for 2 theta, remember, that's what we ultimately found. That sine was negative, cosine was positive, and tangent was also negative. We know that the sine, since some of them are negative, has to be thrown out. Cannot be all positive because 2 of them weren't. And since sine was negative, that's out. Since tangent was negative, that's out. And because we know the only thing left, which does check out because cosine was also positive, would be quadrant 4. Okay, so we didn't even actually need cosine, but given those 2 things, we only had one option. And good, our answer does check out as far as the positive or negativeness. Okay, so that's example 1. A lot of little nuances. Again, most people make mistakes in their algebra, not even the trig parts of it. So just be very careful, be nice, neat, and organized, and pay attention to your details.